Hey students, I got a question here from chapter 2. It's number 66. Maybe I should write on here. Chapter number 2. And it has a graph. And in fact, the question extended on to number 64. Even though 64 is not part of the homework assignment, it's kind of the same logic. So I thought I would kind of do both of these. And so 66, and I'll call 64 a little bonus here. But it says here, this figure, 66, shows the position graph of a particle. So this is important to understand what is being displayed here in the green. This is the position. So this would be saying the position is increasing, so clearly there's some velocity. Then it is decreasing, so it must be moving backwards, have a negative velocity. And then notice this. Notice here it is stationary. See, it's remaining at the position -3 from about 3 seconds to 5 seconds. And then it starts to change its position, starts to get less negative. So that must mean it's moving in a positive direction. And that's what this is after. It says, draw the corresponding velocities. And so I'm going to attack this problem by kind of using a calculus here, I guess, that says the velocity is the derivative of position, okay? And, of course, you also learned in your calculus class that the derivative is, of course, the slope. So, in other words, as I look from maybe 0 to 2 seconds, I could see that the position has a constant slope, the same slope. So that means it would have the same velocity, at least for a time from 0 to 2. And if you look at this slope, you can see it has a rise of 2. So it goes from 0 up to 2, and it does that in 2 seconds. So the slope is just simply 2 over 2, which is a slope of 1. And that's a positive 1. So if I were to, as it says, draw the corresponding graph, and I'll just do it right on here, there should be a constant speed, always having the same slope of 1 from 0 to 2 seconds. Now, then you'll see quickly at 2 seconds, it tends to have a negative slope. So again, slope being rise over the run. Let's see, if I was looking at the rise, it's at 2, goes down 2, and looks like down another 3. And so the slope has a rise of -5. And it does all this from 2 seconds to 3 seconds. So it does it in 1 second. So it must have a speed of -5. Now, -5 doesn't really fit on this graph, so I'll just make one here, -5. And so at 2 seconds, it would be way down here. And so from 2 seconds to 3 seconds, it has a huge negative speed. So that's what I meant in the green when I said its position is increasing, so it has a velocity. Then all of a sudden, it's decreasing, so then it jumps. So it's kind of like comes to a stop and takes off in the other direction. Now, I guess I'll connect a line there, but I think this little kink of discontinuity is trying to say that it happens like really quick. You can't really define a slope that has a kink here. And so I probably should have put a dotted line there. Of course, in reality, any object would have to slow down and start speeding up in the other direction. Now, it may do it very fast, so it would be going, in a positive direction, and then quickly turn around, go the other way. Okay. But by that same logic, if you look from 3 to 5, it's at the same position. In other words, there's 0 slope here. There's no rise. And so from 3 to 5, the speed would be 0. So dot, 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 dot. Okay, and so this object comes in with a speed of 1, quickly turns around, takes off, and has a negative speed, and then comes to a stop. And so now it has a speed of 0 for 2 seconds. And then it looks like from 5 to 6, again, same idea, taking the derivative, that is the slope, it goes from a -3 up to a -2. So for the slope there, it would have a rise of 1, and it did it in 1 second. So there's a speed of 1 again. So 1. Dot, dot, dot. All right, so this motion would be speed of 1, quickly turn around, speed of 5, then it sits there for a while, and then has a speed of 1 coming back in the positive direction. So that would be draw the corresponding velocity versus time. So there's the graph, if you will, for part A. And for part B, what is the acceleration? Now, I'm going to invoke kind of the same thing, that the acceleration is the derivative of the velocity. Okay? And the velocity is this graph in red. So we got red and green. Let me switch to a different color. How about, I'll do black, but the axes are in black, but I don't think you'll confuse that. But I should be now looking at the slope. And so the slope of the velocity. So the slope of the red one from 0 to 2, the slope is 0. So I would have 0 acceleration. Now, technically, this slope from right here at 2 seconds to, I'll call 2 seconds on the negative side to 2 seconds on the positive side, huge negative. So you might say got a huge negative acceleration. But as it goes from 2 seconds to 3 seconds, it has a constant negative speed, so that'd be a negative acceleration. Of course, then the graph, you might say, spikes up with a huge slope, positive. But again, then it just sits there, so then you have a 0 acceleration. I guess it spikes up again right there, but again, 0 acceleration. So most of the time it's 0 acceleration, and that kind of makes sense if you think about from, 0 to 2 seconds, it's going at a constant speed, 0 acceleration. And then from 2 seconds to 3 seconds, again, it's 0 acceleration because it has a constant speed. Now, it's negative. And then from 3 to 5, again, it has a constant speed of 0, so no acceleration. And from 5 to 6, again, it has a constant speed of 1, so again, no acceleration. So other than these little moments of where it changes quickly from a 1 to a -5 and a -5 to a 0 and a 0 to a 1, these little spikes in acceleration, the acceleration is all 0. So when it says, what is the acceleration, and I'm sure they said 0 to 2, so you didn't have to worry about the spike, they want you to say, well, the answer to part B would be, well, maybe I should write it this way, answer to B would be acceleration equals 0 during that time. What happens to the acceleration? Oh, at exactly 2. So I guess there they do want you to kind of say, well, you can't really define it because they don't really give you a, what we would call a continuously differentiable curve. They give you a little kink in it, and the derivative is undefined. So I don't know if they wanted you to be mathematically rigorous and say undefined, or that it would just be a huge negative number, which was what you would need to go from 1 to -5 in just a fraction of a second. So that's really the answer on the homework, but I'll go ahead and show you kind of the same logic here in number 64, since somebody was asking about this. It says, take the slope of the curve of figure 62 to find the jogger's velocity at 2.5 seconds. So 2.5 seconds is right about here on the graph. Okay? Take this, and that's, now, let me backtrack. Notice it's a plot of position versus time. And so velocity is its derivative. And so what they're saying in this problem is just like we did in number 66. So take the slope of the curve to find the jogger's speed at. And we could be wrong here, but I think they're trying to put this at 5 And this one at 20? Looks a little lower than 20 to me, but I think they're just trying to, they don't have little grid lines here, so I don't think they want us to read it too accurate. And I think this is roughly the same slope. Well, let's see, it goes up by 10, and if this is right here, it goes up by 10 in 2.5 seconds. That means it'll go up by 20 in 5 seconds. Yeah, so kind of taking this as one giant slope with a little bit of curve to it, so it kind of matches that out. Again, we can look at the slope as being the rise over the run. And so the rise is 20 meters, I should put, and the run from this is 5 seconds. And so that would have a slope of 4 meters per second, which kind of reminds me on 66. I didn't put any units here, but the rise was in meters and the time was in seconds. And so all of the speeds we were talking about were in meters per second. So this is in units of 4 meters per second. So anywhere along here, the slope is roughly a 4. And so I would say we can say that the jogger's velocity is roughly 4. So at time equaling 2.5 seconds, v equals 4 meters per second. And then repeat this at 7.5 seconds. Now it's 7.5 seconds. And if I again take this whole thing, it's definitely a negative slope. I suppose we might argue that it doesn't come all the way down to a 5. I mean, all the way down to 0. It passes the 5. And so I'm going to put it halfway between. And so when I go to do the slope, the rise goes from 20 down to about 2.5. So let me call it a rise of a negative 17.5. It goes down by 17.5. And it still goes over 10 seconds. And so that's meters and that's seconds. I'm saying 5 seconds because it's from 5 to 10 seconds. And so maybe this one I'll do the calculator here. But a negative 17.5 and divide it by 5 seconds is a speed of negative 3.5 meters per second. So I would say, oh, and it says it must be consistent with this graph. Now I didn't print that up, but let me jump back over to the textbook. Yeah, so the textbook has the speed of about 4 and then about 3.5. Yeah, so it is consistent with that graph. If you've got the textbook in front of you, when you look at the next graph here, which I didn't print. All right, hope that helps. Take care, everyone.